In mathematics, the limit inferior and limit superior of a sequence can be thought of as limiting bounds on the sequence. They can be thought of in a similar fashion for a function. For a set, they are the infimum and supremum of the set's limit points, respectively. In general, when there are multiple objects around which a sequence, function, or set accumulates, the inferior and superior limits extract the smallest and largest of them. The type of object and the measure of size is context-dependent, but the notion of extreme limits is invariant. Limit inferior is also called infimum limit, liminf, inferior limit, lower limit, or inner limit. Limit superior is also known as supremum limit. Limit supremum, lim-sup, superior limit, upper limit, or outer limit. Definition for sequences. The limit inferior of a sequence is defined by or similarly, the limit superior of is defined by or alternatively. The notations are sometimes used. If the terms in the sequence are real numbers, the limit superior and limit inferior always exist, as real numbers or plus or minus infinity. More generally, these definitions make sense in any partially ordered set, provided the suprema and infima exist, such as in a complete lattice. Whenever the ordinary limit exists, the limit inferior and limit superior are both equal to it, therefore, each can be considered a generalization of the ordinary limit, which is primarily interesting in cases where the limit does not exist. Whenever lim-infxn and lim-sup-xn both exist, we have limits inferior, superior are related to big O notation in that they bound a sequence only. In the limit, the sequence may exceed the bound. However, with big O notation the sequence can only exceed the bound in a finite prefix of the sequence, whereas the limit superior of a sequence like e-n may actually be less than all elements of the sequence. The only promise made is that some tail of the sequence can be bounded by the limit superior plus an arbitrarily small positive constant. The limit superior and limit inferior of a sequence are a special case of those of a function, the case of sequences of real numbers. In mathematical analysis, limit superior and limit inferior are important tools for studying sequences of real numbers. Since the supremum and infimum of an unbounded set of real numbers may not exist, it is convenient to consider sequences in the affinely extended real number system. We add the positive and negative infinities to the real line to give a complete totally ordered set, which is a complete lattice. Interpretation. Consider a sequence consisting of real numbers. Assume that the limit superior and limit inferior are real numbers. The limit superior of is the smallest real number such that, for any positive real number, there exists a natural number such that for all. In other words, any number larger than the limit superior is an eventual upper bound for the sequence. Only a finite number of elements of the sequence are greater than the limit inferior of is the largest real number that, for any positive real number, there exists a natural number such that for all. In other words, any number below the limit inferior is an eventual lower bound for the sequence. Only a finite number of elements of the sequence are less than. Properties. The relationship of limit inferior and limit superior for sequences of real numbers is as follows. As mentioned earlier, it is convenient to extend to -infinity, infinity. Then, in -infinity, infinity converges if and only if, in which case is equal to their common value. Since the limit inferior is at most the limit superior, the condition and the condition if and then the interval I, S, need not contain any of the numbers xn, but every slight enlargement, I minus epsilon, S plus epsilon, will contain xn for all but finitely many indices n. In fact, the interval I, S, is the smallest closed interval with this property. We can formalize this property like this. There exist subsequences and for which we have on the other hand, there exists a so that for all. To recapitulate, if is greater than the limit superior, there are at most finitely many greater than, if it is less, there are infinitely many. If is less than the limit inferior, there are at most finitely many less than, if it is greater, there are infinitely many. In general, we have that the lim_inf and lim_sup of a sequence are respectively the smallest and greatest cluster points. For any two sequences of real numbers, the limit superior satisfies subadditivity whenever the right side of the inequality is defined. Analogously, the limit inferior satisfies superadditivity. In the particular case that one of the sequences actually converges, say, then the inequalities above become equalities. Examples. As an example, consider the sequence given by xn equals sin. Using the fact that pi is irrational, one can show that. And an example from number theory is, where Pn is the nth prime number, the value of this limit inferior is conjectured to be 2. This is the twin prime conjecture, but as of April 2014, update, has only been proven to be less than or equal to 246. The corresponding limit superior is, because there are arbitrary gaps between consecutive primes, real-valued functions. Assume that a function is defined from a subset of the real numbers to the real numbers. As in the case for sequences, the limit inferior and limit superior are always well defined if we allow the values plus infinity and minus infinity. In fact, if both agree, then the limit exists and is equal to their common value. For example, given f equals sin, we have lim sup x0 f equals 1 and lim inf x0 f equals -1. The difference between the two is a rough measure of how wildly the function oscillates, and an observation of this fact. It is called the oscillation of effort A. This idea of oscillation is sufficient to, for example, characterize Riemann integrable functions as continuous except on a set of measure 0. Note that points of non-zero oscillation are discontinuities which, unless they make up a set of 0, are confined to a negligible set. Functions from metric spaces to metric spaces. There is a notion of lim_sup and lim_inf for functions defined on a metric space whose relationship to limits of real-valued functions mirrors that of the relation between the lim_sup, lim_inf, and the limit of a real sequence. Take metric spaces x and y, a subspace E contained in X, and a function f. EY. The space Y should also be an ordered set, so that the notions of supremum and infimum make sense. Define, for any limit pointer of E, and where B denotes the metric ball of radius epsilon about A. Note that as epsilon shrinks, the supremum of the function over the ball is monotone decreasing. So we have, and similarly this finally motivates the definitions for general topological spaces. Take x, y, E inner as before, but now let x and y both be topological spaces. In this case, we replace metric balls with neighborhoods. This version is often useful in discussions of semi-continuity which crop up in analysis quite often. An interesting note is that this version subsumes the sequential version by considering sequences as functions from the natural numbers as a topological subspace of the extended real line. Into the spaces n, infinity, sequences of sets. The power set of a set X is a complete lattice that is ordered by set inclusion, and so the supremum and infimum of any set of subsets always exist. In particular, every subset Y of X is bounded above by X and below by the empty set because Yx. Hence, it is possible to consider superior and inferior limits of sequences in. There are two common ways to define the limit of sequences of sets. In both cases, the sequence accumulates around sets of points rather than single points themselves. That is, because each element of the sequence is itself a set. There exist accumulation sets that are somehow nearby to infinitely many elements of the sequence. The supremum, superior, outer limit is a set that joins these accumulation sets together. That is, it is the union of all of the accumulation sets. When ordering by set inclusion, the supremum limit is the least upper bound on the set of accumulation points because it contains each of them. Hence, it is the supremum of the limit points. The infimum, inferior, inner limit is a set where all of these accumulation sets meet. That is, it is the intersection of all of the accumulation sets. When ordering by set inclusion, the infimum limit is the greatest lower bound on the set of accumulation points because it is contained in each of them. Hence, it is the infimum of the limit points. Because ordering is by set inclusion, then the outer limit will always contain the inner limit. Hence, when considering the convergence of a sequence of sets, it generally suffices to consider the convergence of the outer limit of that sequence. The difference between the two definitions involves how the topology is defined. In fact, the second definition is identical to the first when the discrete metric is used to induce the topology on X. General set convergence in this case. A sequence of sets approaches a limiting set when the elements of each member of the sequence approach the elements of the limiting set. In particular, if Xn is a sequence of subsets of X, then lim sup Xn, which is also called the outer limit, consists of those elements which are limits of points in Xn taken from infinitely many n. That is, X lim sup Xn if and only if there exists a sequence of points Xk in a subsequence Xnk of Xn, such that Xk Xnk and Xkx is k infinity. Lim inf Xn, which is also called the inner limit, consists of those elements which are limits of points in Xn for all but finitely many n. That is, X lim inf Xn if and only if there exists a sequence of points Xk, such that Xk Xk and Xkx is k infinity. The limit lim Xn exists if and only if lim inf Xn and lim sup Xn agree, in which case lim Xn equals lim sup Xn equals lim inf Xn. Special case. Discrete metric. This is the definition used in measure theory and probability. Further discussion and examples from the set-theoretic point of view, as opposed to the topological point of view discussed below, are at set-theoretic limit. By this definition, a sequence of sets approaches a limiting set when the limiting set includes elements which are in all except finitely many sets of the sequence and does not include elements which are in all except finitely many complements of sets of the sequence. That is, this case specializes the general definition when the topology on set X is induced from the discrete metric, specifically, for points xx and yx. The discrete metric is defined by under which a sequence of points xk converges to point xx if and only if xk equals x for all except finitely many k. Therefore, if the limit set exists, it contains the points, and only the points which are in all except finitely many of the sets of the sequence. Since convergence in the discrete metric is the strictest form of convergence, this definition of a limit set is the strictest possible. If Xn is a sequence of subsets of X, then the following always exist. Lim sup Xn consists of elements of X which belong to Xn for infinitely many n. That is, X lim sup Xn if and only if there exists a subsequence Xnk of Xn, such that Xxnk for all k. Lim inf Xn consists of elements of X which belong to Xn for all except finitely many n. That is, X lim inf Xn if and only if there exists some n greater than 0 such that Xxn for all n greater than m. Observe that X lim sup Xn if and only if X lim inf Xn c. The lim Xn exists if and only if lim inf Xn and lim sup Xn agree, in which case lim Xn equals lim sup Xn equals lim inf Xn. In this sense, the sequence has a limit so long as every point in X either appears in all except finitely many Xn or appears in all except finitely many Xnc. Using the standard parlance of set theory, set inclusion provides a partial ordering on the collection of all subsets of X that allows set intersection to generate a greatest lower bound and set union to generate a least upper bound. Thus, the infimum or meet of a collection of subsets is the greatest lower bound while the supremum or join is the least upper bound. In this context, the inner limit, lim inf Xn, is the largest meeting of tails of the sequence, and the outer limit, lim sup Xn, is the smallest joining of tails of the sequence. The following makes this precise. Let n be the meet of the nth tail of the sequence. That is, the sequence in is non-decreasing because each n plus 1 is the intersection of fewer sets than in. The least upper bound on this sequence of meets of tails is so the limit infimum contains all subsets which are lower bounds for all except finitely many sets of the sequence. Similarly, let Jn be the join of the nth tail of the sequence. That is, the sequence Jn is non-increasing because each Jn plus 1 is the union of fewer sets than Jn. The greatest lower bound on this sequence of joins of tails is so the limit supremum is contained in all subsets which are upper bounds for all, except finitely many sets of the sequence. Examples. The following are several set convergence examples. They have been broken into sections with respect to the metric used to induce the topology on set X. Using the discrete metric, the Borel-Cantelli lemma is an example application of these constructs. Using either the discrete metric or the Euclidean metric, consider the set X equals 0, 1, and the sequence of subsets. The odd and even elements of this sequence form two subsequences 0, 0, 0, and 1, 1, 1, which have limit points 0 and 1, respectively, and so the outer or superior limit is the set 0, 1 of these 2 points. However, there are no limit points that can be taken from the xn sequence as a whole, and so the interior or inferior limit is the empty set. That is, lim sup xn equals 0, 1. Lim inf xn equals. However, for yn equals 0, 0, 0, and zinc equals 1, 1, 1. Lim sup yn equals lim inf yn equals lim yn equals 0. Lim sup zinc equals lim inf zinc equals lim zinc equals 1. Consider the set X equals 50, 20, minus 100, minus 25, 0, 1, and the sequence of subsets. As in the previous two examples, lim sup xn equals 0, 1. Lim inf xn equals. That is, the four elements that do not match the pattern do not affect the lim inf and lim sup because there are only finitely many of them. In fact, these elements could be placed anywhere in the sequence. So long as the tails of the sequence are maintained, the outer and inner limits will be unchanged. The related concepts of essential inner and outer limits, which use the essential supremum and essential infimum, provide an important modification that squashes countably many interstitial additions. Using the Euclidean metric, consider the sequence of subsets of rational numbers. The odd and even elements of this sequence form two subsequences 0, 1/2, 2/3, 3/4, and 1, 1/2, 1/3, 1/4, which have limit points 1 and 0, respectively, and so the outer or superior limit is the set 0, 1 of these 2 points. However, there are no limit points that can be taken from the xn sequence as a whole, and so the interior or inferior limit is the empty set. So, as in the previous example, lim sup xn equals 0, 1. Lim inf xn equals. However, for yn equals 0, 1/2, 2/3, 3/4, and zinc equals 1, 1/2, 1/3, 1/4, lim sup yn equals lim inf yn equals lim yn equals 1. Lim sup zinc equals lim inf zinc equals lim zinc equals 0. In each of these four cases, the elements of the limiting sets are not elements of any of the sets from the original sequence. The omega limit of a solution to a dynamic system is the outer limit of solution trajectories of the system. Because trajectories become closer and closer to this limit set, the tails of these trajectories converge to the limit set. For example, an LTI system, that is the cascade connection of several stable systems with an undamped second-order LTI system, will oscillate endlessly after being perturbed. Hence, if the position and velocity of this system are plotted against each other, trajectories will approach a circle in the state space. This circle, which is the omega limit set of the system, is the outer limit of solution trajectories of the system. The circle represents the locus of a trajectory corresponding to a pure sinusoidal tone output, that is, the system output approaches, approximates a pure tone.